This video is on the section 2.4 notes, operations with functions. So the first four operations we're going to look at are just typical addition, subtraction, multiplication, and division. And we have the notation here with functions that would probably be more comfortable. Addition would be f of x plus g of x. You're adding the functions together. F of x minus g of x, you're subtracting them. F of x times g of x, f of x divided by g of x. And then over here we have kind of like the shorthand notation, which is maybe even a little bit more common. So f plus g of x, f minus g of x, f times g of x, f divided by g of x. And it just makes it so you have to write the x one time instead of two times. The notations are equivalent, but it's really common for students to kind of understand this notation over here and get confused by this. So what I did throughout the notes is only use this notation over here that's maybe a little bit more common, maybe a little bit more shorthand. You can see here they have f plus g, f minus g. That's like really shorthand. They just completely dropped the x's. It doesn't mean the procedure is any different. It's just shorthand. That's all it is. Okay, so first, this notation right here for this example is saying take the function f of x, take the function g of x, add them together, but for the x you're going to be plugging in 4. So this means take f of x, plug 4 into it, take g of x, plug 4 into it, and add those results together. So f of 4 is 3 square root 4 minus 2. And I didn't just make that up, I'm getting that from the instructions right here. So f of x is this function, so I plugged in 4. 3 times the square root of 4 is 3 times 2. 3 times 2 is 6. So 6 minus 2 is 4. All right, and then g of 4 is 4 squared plus 5. 4 squared is 16. And 16 plus 5 is 21. So we are adding these together. F of 4 plus g of 4 is 4 plus 21, which is 25. Right, the next one says take f and g and subtract them, and don't plug anything in, just leave it as x. So I'm going to write f of x. I'm going to subtract off g of x. And let me start here with f of x, subtract off. And the thing you have to be careful of is to make sure that whatever function you are subtracting off, you're putting in parentheses so that you can distribute the negative. You have to make sure that you're going to be subtracting each term in that function. So make sure you put parentheses around that. So we have 3 root x minus 2, and then minus x squared minus 5. And when you write an expression like this, it's proper to put the highest exponent of x first. That would be x squared. This exponent of x, if we wrote it as an exponent instead of a radical, it would be x to the 1/2. So I'm going to write negative x squared, then a positive 3 root x next. And then I can combine my like terms and have negative 7. Next, it says f times g of 0. So this is f of 0 times g of 0. So f of 0 is going to be 3 times the square root of 0 minus 2. 3 times the square root of 0 is just 3 times 0. And anything times 0 is 0. So we have 0 minus 2, which is just negative 2. G of 0 is going to be 0 squared plus 5. 0 squared is 0. so that's 5. And then what we're doing is we're multiplying those together. So negative 2 times 5 is negative 10. Next, they say we're dividing f divided by g of 9. So this is f of 9 divided by g of 9. So this would be 3 times the square root of 9, which is 3 times 3. And so we have 9 minus 2, which is 7. G of 9 is 9 squared plus 5. So that's 81 plus 5, which is 86. So we have to write these as division, 7 divided by 86. And I don't believe 86 is divisible by 7. I don't think we can reduce that. Yep, 7 over 86 is the simplified fraction there. Okay, now I want to show you a little trick on your calculator that's kind of cool for these. So I'm going to put the functions into my calculator. I'm going to press the y equals button, and I'm going to type 3 square root x minus 2 for my y1. And then for y2, I'm going to type x squared plus 5. And then on my paper, I'm going to write down, this is my y1, this is my y2. Okay, now here we were doing f of 4 plus g of 4, which would be y1 with 4 plugged in and y2 with 4 plugged in. So what we can do is we can actually let the calculator do these calculations for us. We can do alpha calc. So I did the green button, and then calc over here, alpha calc. I have y1 of 4, plugging 4 in, and then alpha calc, y2, plugging 4 in. So this is my calculator's way of doing f of 4 plus g of 4. The answer is 25, which is what I got. I can't do this one. This one has to be done by hand. This one over here, I can do this. So I'm going to go back up here because I don't feel like typing this again. 0, 0, and this time we're multiplying. So f of 0 times g of 0, negative 10. And then next we have to divide them. F of 9 divided by g of 9. Turn that back into a fraction, and there we go. So your calculator is really good at these. Now, this is not how I would do my work necessarily for a testing situation, because in a testing situation, I'm probably going to say show all of your intermediate steps. You know, show plugging in 4, show plugging in 4, show that you have to add them, show that you understand. But this is a great way to check your work and make sure your answer is right. Okay, next problem says, find each function, so we're going to do these different operations, but state the domain. And remember, the domain is just the x values that you can possibly plug into a function. So before we even get started doing the domain for these different functions that have been combined, let's look at the functions before they have been operated on. So we have f of x is square root x. G of x is 3x plus 1, and h of x is x minus 1. So these two functions right here are just straight lines. 3x plus 1 has a y-intercept of 1 and a slope of 3, y-intercept of negative 1, slope of 1. These are just lines. And for a straight line, you can plug in any x value you want. Negatives, positives, everything's going to work. Now here with the square root sign, our domain's a little bit limited. We can square root 0, we can square root positives, but we can't square root negatives. So the domain is a little bit limited for this one. So I'm going to say 0 is the lowest number that I can square root, and then any positive numbers. I'm going to keep these in mind as I go through and do these examples because it's going to help me find the domain for these kind of combined functions where it's two of the functions written together. So f plus g means f of x plus g of x. And so here f of x is square root x, g of x is 3x plus 1. None of those can be combined, and so this is just my answer. And so now I need to say what the domain is. So I have one piece that's all real numbers. I have one piece that is 0 to infinity. And the way I like to think of this is like you're having a dinner party with your friends, and you have some friends, maybe most of them, who will eat anything that you make, and you have another friend that won't eat any kind of pasta. So when you make something at that dinner party, you have some friends that'll eat anything, some friends who won't eat pasta. You're probably going to go with some sort of food that doesn't involve pasta. Whatever the domain is, you're going to go with whatever's the most limited. So here, if one option is all real numbers and one option says only 0 to infinity, we're going to stick with 0 to infinity. All right, let's try the next one. It says g divided by f. So this is g of x divided by f of x. G of x is 3x plus 1. F of x is the square root of x. I'm not going to simplify anything about that. I'm just going to leave that the way that it is. A lot of times when we have functions divided like this, that's how you can do it. You can kind of leave them. So when we deal with fractions like this, what we have to be careful of is that we can't divide by 0. You can divide by negative numbers, you can divide by positive numbers, but you can't divide by 0. So I'm going to write that as a note to myself. Can't divide by 0. So since I have a square root in here, it's kind of like the previous problem. One piece of the problem was all real numbers. The other part was 0 to infinity. And so I said, what's the most limited? 0 to infinity. I would say the same thing here. The top is all real numbers. The bottom is 0 to infinity. Let's go with 0 to infinity. However, we have to be careful because the bottom says you can include 0. The square root does. But since this is a fraction, we can't include 0. So I would start off by saying, my square root makes me think that I should say 0 to infinity. But because this is a problem with a fraction, I'm going to erase this. And I'm going to say, well, keep it like this, but just don't include 0. Because this is part of a fraction and the square root's on the bottom, we just don't want to have 0 on the bottom of a fraction. So exclude that part, and then the rest is the domain. Okay, for the next one, we've got multiplication. G of x times h of x. So g of x is 3x plus 1. H of x is x minus 1. Whenever you have two functions that you're multiplying, you are almost always going to have to put them in parentheses. And then there'll be two parentheses right next to each other, and you'll have to FOIL them or distribute them somehow. So I can FOIL these, so I'm going to go ahead and do that. 3x times x is 3x squared. 3x times negative 1 is negative 3x. 1 times x is x. 1 times negative 1 is negative 1. So that gives me 3x squared minus 2x minus 1. When I look at this, I have all real numbers and all real numbers. And then my resulting answer is a quadratic. That's one of those graphs that's kind of a U shape like this. And the domain for that is all real numbers as well. You can plug in anything you want, negatives, positives. So there's no reason to think that my domain should exclude any x values based on this. All the x values are going to be fine. All right, last, g minus h. So this is g of x minus h of x. So g of x is 3x plus 1 minus h of x is x minus 1. Remember, whenever we subtract, I should put it in parentheses to make sure that I am going to subtract each of the terms. So I'll distribute that negative. 3x plus 1 minus x plus 1. So that gives me 2x plus 2. When I started the problem, each of my two functions that I was working with had a domain of all real numbers. When I look here at my result, this is a linear function, 2x plus 2. It has a y-intercept of 2 and a slope of 2. Straight lines have a domain of all real numbers, so I would expect that this domain is still just all real numbers. Nothing has happened that makes me think it should become more limited. All right, next, we have a type of operation, a different type of operation that you might not have seen before, and that's composition. And composition just means that you're going to take one function and plug it into another function. So here, f of g of x, that's how you write this. F of g of x is how you read that out loud. It means that you take the function g of x and you plug it in for each of the x's in f of x. That's what that means. Or here, g of f of x means that you take f of x and plug it in for all the x's in g of x. So that's what composition means to take one function, plug it into another function. So first, we're going to kind of start off easy. We're going to look at doing this with relations, where it's just a set of ordered pairs, and we're going to see how that kind of works. So f of g of 1 means f of g of 1. And whenever we do this, we kind of work from the inside out. So I'm gonna use a color when I do this. Okay, so g of 1 is 4. And so now I'm just doing f of 4. F of 4 is 9. And so this result is 9. Okay, this notation means f of g of 2. So I'm going to start with g of 2. If I take g and I look at where x equals 2, the result is 5. And so that means next that I'm looking for f of 5. So if I go over to f, think about plugging in an x value of 5, the output is 10. And so this answer is 10. All right, g of f of 3 says start by plugging 3 into f. So if we look at an x value of 3, the output is 1. And then take that and let it be the input into g. So that's the x and g, and the output here would be 4. This one says g of f of 5. So we would start with f and plug in 5. So f, plug in 5, you get 10. And then looking at g and an x value of 10, I can see it's not in the list. There's an x value of 1, an x value of 2, and an x value of 3. X value of 10 is undefined. And so this result is undefined. There's no answer for that one. Okay, so now we're going to do the same thing, but we actually have equations to work with, equations to plug numbers into. So this notation means f of g of 5. So we're going to do the same thing. We're going to start with that inside function, g of 5. So g of 5 is 2 times 5 minus 1. which is 10 minus 1, so that's 9. So what I'm going to do next is I'm going to take that 9 and plug it in here, and to finish the problem, I'm going to do f of 9. And now I can do f of 9 is the square root of 9, which is 3. So my final answer is 3. This notation means h of f of 5. So I'm going to start off with that inside function, f of 5. And f of x, f of 5 is the square root of 5, okay? And then I'm going to take the outside function h and plug 5 into it, h of the square root of 5. So h of the square root of 5 is the square root of 5 squared. And here we have a square root and a squared, and those cancel out, and we get that that equals just 5. Or you could think of it as square root 5 times square root 5 is square root 25, which is 5. Okay, here we have h of g of f of 9. So we're going to start from the inside and work our way out. So first we have f of 9. So the square root of 9 is 3. And so that leaves us with h of g of 3. And then we're going to work on the next piece, which is g of 3. G of 3 is 2 times 3 minus 1, which is 6 minus 1, so that's 5. And so then that would leave us with h of 5. And h of 5 is 5 squared, which is 25. What's cool about your calculators is your calculator can actually handle doing this one as well. So I'm going to type these into the y equals screen. Square root x, 2x minus 1, x squared. And then I'm going to write down, this is my y1, y2, y3. And when I type this into my calculator won't make it look like this. It'll make it look like this. So for this first one, I'm going to do y1 of y2 of 5. So alpha calc y1 of y2 of 5 is f of g of 5, and it gives me 3. H of f would be 3 of 1. So 3 of 1 of 5 is 5. And then this one would be 3 of 2 of 1. So 3 of 2 of 1 of 9. Make sure you get all your parentheses in there. Okay. 25. So again, you'd have to show your work. That's not showing your work, but you can use it to check your answer, which is nice. Okay. Next, it says find each composition function. We're not plugging in numbers this time. We're just doing the composition. Find each composition function and then state the domain. Okay, so we're going to do kind of what we did last time. We're going to start down here. F of x is square root x. G of x is 3x plus 5. H of x is x minus 1 squared. Okay, so we have a straight line. We know the domain of a straight line. is negative infinity to infinity. X minus 1 squared is a quadratic. It's just written in a different form, but I'll improve it to you. X minus 1 squared. There you go. You can see it's a quadratic. So again, the domain is all real numbers. You can have all the negatives. You can have all the positives. Okay. And then here we have that square root, and we know that with the square root, we can't have negatives. We can only have 0 and positives. So whatever ends up happening, we know that whatever these functions are, we're going to have to keep this in mind for how we plug something in. Okay, domain is plugging something in. All right, so f of g is just shorthand notation. That means f of g of x. It's saying take f of x and plug g into the inside. Okay, so I'm going to start with f of x. And then I'm going to take g of x and I'm going to plug it in on the inside. So I'm taking f of x and I'm plugging g of x on the inside. Okay, so if I look at this, I have to think about what I'm plugging into the inside. So what I'm plugging into the inside is a domain of all real numbers. I'm plugging in 3x plus 5. 3x plus 5 is a domain of all real numbers. So that's where my domain is starting. But then I have to look at my result, my answer. My answer is square root of 3x plus 5. That's going to limit my domain because it's got a square root sign. I'm taking something that could have any number plugged into it, but I'm sticking it inside of a square root where I'm not allowed to plug in anything I want. I can't plug in negative numbers. So I'm going to say that this thing that I plug in, the 3x plus 5, has to be greater than or equal to 0. Has to be positive, or it can equal 0. 0 is fine. And then I'm going to go ahead and solve this. So I'm going to subtract the 5 over, and then I'm going to divide the 3 over. So x has to be greater than or equal to negative 5/3. So if we did negative 1, plug in negative 1, 3 times negative 1 is negative 3. Negative 3 plus 5 is 2. Square root of 2, that's totally fine. You can plug that in. But if I tried to do, let's say, negative 2 is less than this. 3 times negative 2 is negative 6. Negative 6 plus 5 is negative 1, and I cannot square root negative 1. So I know that my original domain should have been all real numbers because this is what I was plugging in, and that's what domain means. It's what I plug in. But then when I looked at my composition, I could see it added a square root to the problem, and so my domain had to become a little bit more limited to reflect that. And so then I kept in mind what I knew about square roots, and I said, okay, the inside of a square root has to be greater than or equal to 0, and that's how I found it. So my domain is negative 5/3 to infinity. And typically when I write these answers, when I've done the composition, I'll usually just box this part. You can box the rest of it. This is just notation, but this part is the answer. So this is what I need to see, and then the domain. This next function is g of f of x. So we're starting with g of x. And we're plugging f of x inside. So starting with g of x and plugging f of x inside. Now, since the function that I'm plugging in is the square root of x, I'm going to look over here. The domain that I'm starting with as my input is from 0 to infinity. And then I'm going to look at my resulting function, 3 square root x plus 5, and just see if this function on its own looks like it should be more limited than that. And I don't see any reason for that to be the case. It's not in a fraction form where I should not include 0 or something like that. So I'm just going to say that this domain is from 0 to infinity because I plugged that square root in. Now for this, like I said on the previous problem, you can include this notation, or you could just put a box around this as the answer, or you could go back and you could say g of f equals this and say that's the answer. The important part is just this. This part over here is just notation. Okay. Let's get to the last little bit here. So I'm going to leave this page handy. This says f of h. So f of x is the square root of x, and we're plugging h of x inside. I didn't leave very much space there. We're plugging h of x inside. So taking f of x and plugging h of x inside. All right, so if I look at this, the squared and the square root are going to cancel each other out, and I'm left with just x minus 1. That's a straight line, a linear equation. If I think about the functions I plugged in, x minus 1 squared has an input. What I'm plugging into the other function is all real numbers. So what I was plugging into the square root was all real numbers. So that's what I'm starting with my domain. And then I look at this result, x minus 1, and I see if there's any reason to limit that domain from there. And this is a straight line. There's no reason for me to limit that domain. So I'm going to leave this as the answer. I'm just going to say f of h is x minus 1. And I'm going to say the domain is negative infinity to infinity, all real numbers. All right, this next one is kind of like a double composition. So it says f of g of g. So I'm going to ignore the f on the outside. First, I'm just going to take g and compose it with itself. I'm going to plug g into itself. So I'm going to have g I'm plugging g into itself. And so when I do that, that means that I'm plugging in 3x plus 5 into itself. Okay, so this gives me 9x plus 15 plus another 5. So 9x plus 20. Okay, so now what I'm doing is I'm going to take f of x, and then this is what's being plugged into f of x. So f of x is the square root of x. And I'm going to take all of this and plug it in here. Okay, so now when I think about what I plugged in here for my domain, this is all real numbers. So I took something that was all real numbers, I plugged it into here. When I simplified it, this is the equation of a straight line. It has a slope of 9, it has a y-intercept of 20, so this is still all real numbers. When I take this and plug it into this function, I'm plugging in something that has a domain of all real numbers. The input has all real numbers, so that's my expectation when I get started. But now what I'm looking at is my resulting function has a square root over it, and I know that if I have a function that's got a square root, it should be limited because I can't square root negative numbers. So even though my input function allowed everything, it allowed negatives, positives, everything, I know that this equation has become limited because of that square root sign. So I'm going to say that this part that I input, the 9x plus 20, needs to be limited so that it's only positive numbers, those that are greater than 0, or those that are equal to 0. And then I can go ahead and solve for x. So I'll subtract the 20 over to this other side and divide 9 over to the other side. And so this is my function. And the domain for this composite function is negative 20/9 to infinity. All right, now for these last couple examples, we are trying to recognize composite functions. We're trying to recognize what the composition was created from to make some other function. So we have y equals the square root of x minus 3, and it was created by one of these three functions being plugged into another one. So if I look at this problem, I can see that we've got a square root. I can see that that square root has an x minus 3 under it. So if I think about this, I can think of the square root as the outside function. I can think of the x minus 3 as the inside function. So the inside function looks like it's g of x. The outside function looks like it's f of x. And so this composition would be f of g of x, or f of g. And you can say fog for short. Some people do. I generally don't, but you could say that. This next one says 2x minus 6. And this one is kind of maybe a little bit harder to recognize. That one I feel was pretty straightforward. But here, it's definitely got to be these two. We don't have a square root there, so I'm looking over here and I'm thinking, how could I get that 6? How could I get the 2x with a minus 6 on the end? And that's if I started with this function right here and I did 2 and multiplied it by something else. And if the thing that I multiplied it by was the x minus 3, then when you distribute the 2, you could get 2x minus 6. So we have 2, and the inside function would be g of x. So the outside function is h, the inside function is g of x, so we have h of g. This next one is a little bit harder to recognize because it's not just one composition like this, it's actually two compositions. So the first step is to look at this part right here and ignore the minus 3. If we just look at that part, we can see that that's got a 2x, but it looks like the square root was plugged into it. So we can start with that. We can say this is 2 times something. The something that it's being multiplied by is f of x. So 2 times something, the something that's plugged in is f of x. That means that we have f of x as the inside function and h of x as the outside function. But we're not done. That only gave us the 2 root x. That did not give us 2 root x minus 3. So they must have taken this and plugged this into g of x. They must have plugged it in to x minus 3 and stuck this in here. So if the 2 root x was plugged in here, 2 root x minus 3, that's h of f of x being plugged into g of x. So this is g of h of f of x, and you can say g of h of f of x.